So today we're going to talk about graph neural nets and some library called PyTorch Geometric for processing such kind of neural networks. So this talk will be a very introductory, some basics regarding graph neural nets for those of you who never worked with them. The agenda would be a very quick introduction to geometric deep learning, which is a special type of deep learning algorithms or area of research of deep neural nets related to processing some specific types of data, which we will talk about next. Some specific architectures like graph neural nets. The key idea behind graph neural nets, which is called message passing. We will talk about it more. And introduction to one of the libraries for processing of such architectures, PyTorch Geometric. It's not the only library. There are other libraries for processing graph neural nets, but we will use PyTorch Geometric for just demonstration purposes. And we will see how to write a very simple graph neural net in PyTorch Geometric. Yep. Start recording. Now we're recording. Okay, so this is our agenda. Again, quick introduction to geometric deep learning, graph neural nets and message passing, and a hello world application using PyTorch Geometric, a very simple graph neural net. Okay, let's start from the basics. Let's recall what is deep learning. Of course, it's a multi-head beast with a lot of different applications and different types of neural nets. But in most of the cases, we can consider deep learning as a way of constructing algorithms, which we call models, which transform data from some input to some output, basically a mapping from X to Y. These models has some parameters, and these parameters are adjusted during the training procedure. And usually we train these models with supervised learning, meaning we have correct answers for our input. So for this input, I want this output. And we then run our models at inference stage, and these models producing the correct results because they are trained to do so. But the question here is, what kind of model can we use, and what kind of data can we use as input, as output? So let's consider different cases. So the simplest case, we have just simple data, some vectors, some low-dimensional information pieces. And for that, we can use some classical machine learning approaches or multi-layer perceptrons, or you can call them fully connected neural nets. Very simple, right? But what if we have something more complicated, like images or videos? So which type of neural nets do we use for images? Who knows? Right, convolutional neural nets. Images, videos, audios, something where we have a signal and we have local features when we want to extract some local information around some points. For text, audio, and sequences, for audio, you can see that we have both recurrent neural nets and CNNs. We can have different combinations of these networks, recurrent neural nets, and recently we have transformers for natural language processing, for translation, etc. But for graphs, what do we have for graphs? Okay, so we can try to apply, for example, multi-layer perceptron or fully connected networks. But what's the problem, for example, for applying FC, fully connected networks, to graphs? Well, first obvious problem is that graphs can have multiple different variations and it can have variable length. So we can have graph with 10 nodes or 20 nodes. It's not obvious how to pass them into this multi-layer perceptron with fixed input length. We can try to apply recurrent neural network, but recurrent neural network suppose that you have some order, but in graph is unordered structure mostly. So you don't have a specific order how you pass your graph, right? Convolutional neural nets, a bit closer, because for convolutional neural nets, it's important what are the features in a local region of your image or a video. In graphs, you can also think of, hey, I have these neighbors around my node, and I want to use these informations to somehow aggregate this information and to calculate something within a node. But you cannot apply CNNs like straightforward to graphs, because CNNs are for matrices, for tensors, for something which we also call Euclidean data structures. But graphs are non-Euclidean data structures. There are no vectors, no matrices, no tensors. So it's a bit more complicated structure. What are the examples of graphs and what kind of tasks can we have with graphs? Well, you can name a few yourself, but some obvious examples, molecules, some biological science. In biological science, you have, for example, connectomes, things which has some nodes and some connections. You can think of drug discovery. How can we find a new type of molecule for treating some diseases, etc. So everything related to biology and chemistry. Also, you can think of social graphs. For example, a node could be a human or a person, and a connection would be a friendship relations or something else. Or you can think of a set of different documents and links between those documents, and so on. And third kind of set of tasks is processing of 3D data, 3D models, meshes, etc. That's not the ultimate list. You can think of any other types of tasks where you also can have graphs. A bit more terminology about graphs. So a graph is a set of nodes and a set of edges between those nodes. An edge can have a direction, or it can be unidirectional, or you can think of bidirectional. So it can point from node 1 to node 3 and backwards, from node 3 to node 1. If we're not drawing any arrows, that means that it's a undirected graph. If there are some arrows, that means it's a directed graph. We can think of nodes as a set of things. Here it is represented as a vector of some entities, but important thing is that in graphs, the order is not important. So every operation which we perform on graphs should be invariant in terms of some permutations. So there is no strict order like 1, 2, 3, 4, 5. We can order these nodes in any order, but we must preserve ordering between nodes and corresponding edges. So we need to consider this information when we process graphs. Okay, so for nodes, we simply can stack them into a vector in some order. But what about edges? How do we store information about edges? There are multiple ways of storing information regarding edges, but one way is to store edges in adjacency matrix. It's a square matrix for simple graphs. The dimensions of this matrix is a number of nodes per number of nodes. It's a square matrix. And in each element of this matrix, you have either 0 or 1. And 1 means there is a connection between node J and node I. If it's an undirected graph, then this matrix will be symmetric because you have a connection from J to I and from I to J. That's why it is a symmetric matrix in this example. Another example of a graph, it is directed graph. You have arrows here. And this means that, for example, in adjacency matrix, it's not symmetric anymore. We have some ones and some zeros. And for example, connection from node 1 to node 3 is represented as 1 in this matrix with row 1 and column 3. So again, from node 1 to node 3, row 1, column 3. That's the one in the adjacency matrix. And there are other ways of representing adjacency matrices or edges in our graph. For example, this graph connectivity can be also expressed in this compact form, also called COO format or coordinate format. The dimension of this matrix is 2 by number of edges, and each column just represents the pair of corresponding nodes. For example, we have again this connection from 1 to 3, and we have this 1, 3 pair. And the order is not important in this matrix, right? Because there is no specific ordering of these edges. So these are the bases of graphs, and this will be used in our future demonstration. Now, let's talk about graph neural nets. So we want to process graphs somehow. That means that we need some model, some deep learning model, where as input we pass our graph and it outputs something. There are different possibilities. What can we output as output? It could be another graph, or it could be some vector or a value. For example, we want to do classification over graphs. That means our output will be just a label or a vector of distribution over classes. Or you can do regression. That means the output would be some tensor or vector. In other case, we want some graph as output. In simplest case, we want the same graph, but for each node, we want to transform the data somehow. There's a kind of different possibilities. But first, what we need to do, we have like a raw graph, but we need to assign some information, some data to its entities. For example, the simplest case, we want to assign some vector, feature vector to each node. In a more complicated scenario, you can also have feature representation for edges, right? But in simplest case, you have just nodes. For each node, you have some feature vector. It could be actually not a vector. It could be any type of data. You will just need to have a way to process the data. For example, it could be an image or a text, anything. You just want to have some local transformation function for this type of data. And then you can apply like graph notation on top of that. So let's, for simplicity, consider just raw feature vectors for each node. And we have some edges. Edges could be represented as an adjacency matrix or as a COO connectivity matrix. Now, how do we process graphs? Our first step would be to take the graph and produce another graph. And here are some possibilities. In the simplest case, within this transformation, we want to obtain the same graph in terms of the topology, but each node will have different feature vectors. So basically, we're transforming feature vectors within that graph, but taking into account the connectivity of different nodes between each other. And then we repeat this procedure. And you can think of these arrows as layers. Like in general, in simple neural nets, you have layer 1, layer 2, etc. And for example, in PyTorch Geometric, when you construct graph neural nets, such transformations also usually treated as different layers. So in simplest scenarios, the graph will remain its topology and structure, but the features will be changed somehow. Or in more complicated cases, we can have also transformed graph somehow at the output of such layer. For example, there are some pooling operations where as output we get a reduced graph, or unpooling operations where we get larger graphs. But in simplest case, the graph remains. And another opportunity, we can have a global pooling where as input we have graph, and as output we have something single, like a single vector, single value, single tensor, but with no graph as output. But let's consider first the simplest types of operations when we have graph as input, graph as output. What's the basic idea of processing graphs? Well, of course, we can just apply some transformation for each node, right? But in this case, we will not have any aggregation of information from neighbors, from other points. Let's consider some aggregation of information. The simplest way of aggregate information is to consider neighbor nodes of current node. For example, we want to compute new value for the node which is orange here, and we want to use its neighbors. And the mechanism behind this is called message passing. So it's a key idea in graph neural nets. It's just called message passing. And the idea is that we basically pass some message from neighbors to this node and aggregate the result and update the feature vector of this node. In more details, let's consider our target node, xi, and some neighboring node, xj. And there is an edge, eji. And usually, I means target node, and j means some neighboring node, or the source of information. We can define a function which takes xi, xj, and the edge. And this function is basically the message from xj to xi. It could be any function, and important thing is it is a trainable function, a learnable function. So when we will construct the graph neural net out of it, we will train it end to end, and the parameters of this function, hidden parameters of this function, will be updated during the training. Now, we have right now the function which passes the message from one node to another node, but we also have some set of neighbors for this particular node, and we need some function to aggregate this information. So this unification sign just means some way of aggregating this information. An important property of this aggregation function should be invariance in terms of a permutation of the neighbors. So we can pass neighbors in any order, and aggregation function should return the same result. The simplest examples could be like averaging or taking maximum value, etc., like in pooling operations. And finally, when we calculated aggregated message from all the neighbors, we calculate some update. We take all the information coming from neighboring nodes, we take our current feature vector and pass it to another function, which is could be also trainable, and we update the value of xi. And that's the simplest and more as general as possible representation of a graph neural net layer. This mechanism, again, is called message passing. And then we can start modifying these things and start to, for example, selecting different functions for phi, for gamma, and for this u operator. And depending on which particular representation of this function we choose, we get different types of layers of graph neural nets. And there are dozens of papers available, and different papers use different functions, and you have different certain implementations of the graph neural net layers. One simple example, let's say we have a set of neighboring nodes, xj. For each feature vector, we apply simple linear transformation, meaning that we multiply them by matrix W. That will give us another representation of each neighboring node, W multiplied by xj. Then as aggregation, we will take some simple summation, and you see that under this sum we have j's, those indexes j which are neighbors of node I. And after the summation, we just pass it to some activation function like ReLU or sigmoid, and that's it. And then we just assign it to x. And let's take one step back. The important note is that we will do this operation for each node, but in parallel. So each node will run this operation synchronously. So it's not like we calculated this operation for one node, then we move to the next node and use this updated information. No, we calculate everything in parallel in synchronous mode, right? This is the simplest example. And you can see some relation to a convolutional operator here. So what's a convolution, right? We have our pixel in 2D images. We have some neighbors. We multiply these neighbors by some weights. We aggregate them together, and this is the result for this location. And we perform this for multiple locations. So this is very similar here in graphs. We have neighbors, multiply them by some weights, aggregate them together, and do this for every location. That's why these types of graph neural nets or types of graph neural net layers, sometimes called convolutional graph neural nets with some modifications actually. And as I said, there are different variations of these functions. So message passing protocol is a general representation, but we can have different types of messages. For example, what I showed you previously, it's kind of called convolutional graph neural nets, but in some particular papers, there are actually a bit different formula, a bit more complicated, but the idea is similar. We can have a bit more complicated ways to pass message. For example, using attention mechanism. What's attention mechanism in, for example, in in NLP? It means that when we aggregate results from different nodes or from different words in NLP, we calculate different coefficients for different parts. And here we also can calculate different importance coefficients for different nodes. Using the same attention mechanism, you can, for example, pass a feature vector of your node and feature vector of your target node to some neural net, which will produce the coefficient, the importance coefficient of this particular neighbor node. And then you can pass it to softmax and just get a coefficients. And then you when you aggregate, you not treat all of them equally, but you multiply them by some coefficients. That's an attention mechanism. And there are different variations. There are a lot of different papers. This is a very rapidly changing field. And basically, people are trying to invent some new ways of passing messages or different ways of calculating aggregation. The simplest cases are calculating average or mean, or using maximum value or something else. Also, for the update, you can think of something more complicated. For example, you can multiply just the result vector by some matrix and then pass it to this node. This will be linear. Or you can think of a more complicated thing like RNN. What does it mean? Well, remember this formula for the update. And you can think of these updates which are coming to xi as a time series, right? So you run this thing layer by layer, and for each layer you have, for example, same coefficients, and you have time-sampled data, the aggregated message from neighbors. And you can pass this gamma to some recurrent neural net or GRU or LSTM, and you can take into account the previous information from previous timestamps, right? So different ways of calculating xi, different ways of update. And potentially some other things. For example, pooling. We didn't consider pooling here, but you can think of a pooling as constructing a new graph, for example, reduced graph by some algorithm with some new features. Or a global pooling, where you have a graph as input and some, again, value or tensor or vector as output, but without a graph. So you lose all your topology. You just generate some single value or single vector, which is useful, for example, for classification of graphs. And usually you will have this as output of your network. Now, we will see some example in PyTorch Geometric. But first of all, I'd like to say a few words about some basic principle behind PyTorch Geometric. So it is based on a library called PyTorch. Probably you've heard of it. You can implement different types of neural net in PyTorch. And it has some features like automatic differentiation, a good way of creating new layers, etc. And this basis is taken from PyTorch Geometric and the library called, this basis was taken from PyTorch, and the library called PyTorch Geometric was created on the basis of it. And we have the same notation of backpropagation, data set management, training loop, everything is the same. The only difference is how do we construct our data representing graphs, and how do we construct particular layers responsible for graph neural nets. But everything else is the same as for regular neural nets. Okay, let's see some example. So this PyTorch Geometric has some hello world data sets, some simple data sets which you can try and train your very simple neural nets. For example, there's a data set called enzymes, which is a collection of some molecules, right? And this is a classification task. So as input, you have different molecules, and you want to classify to one of 6 classes. For example, let's take the data set is a collection of these graphs. Let's see what is like one item of this list. So this is a representation of a single graph. What do we see here? So for example, edge index represents this 2 by number of edges matrix. It means that in this particular graph, we have 168 edges, and X is our feature matrix. This means that we have 37 nodes, and each node has a vector associated with it with 3 components. So each of 37 nodes has a feature vector of size 3. And since it's a classification task, we have only a single label, Y, which is 1, meaning that, well, it's not a value, but it's a dimension, like it's just a single scalar. This is an example of graph. You can construct your own data sets with your own representations, but this is the commonly used in PyTorch Geometric. Next, we have a data loader. One of the main features of that, it can produce batches of your graphs. Because if you can think of batches, it's not so trivial, for example, as vectors and images. In images and vectors, you just stack them together by another dimension, and that's your batch. How do you deal with graphs? How do you construct batch? Actually, it's pretty simple. You can just put all of your graphs like together, and you can think of it as just one giant graph. It just means that between these two graphs, you have no connections, no edges. But the set of nodes is aggregated all together, I mean, in the unified set of nodes. Edges as well, they are preserved. And the only difference is that we need to track which nodes correspond to which initial graph. For example, it will be used later when we will do pooling operation, but we will need this only for a specific subgraph. So again, let's use this data loader to create a batch, for example, for size with size of 4. And let's take just one example. So data is the object containing the whole batch, and it will has, let's see, it will have the edge index x, y, and also another field called batch. And we also print the batch here, and you will see that this tensor, the last tensor, just represents the labels of the graphs within that batch. So we have batch of 4 graphs, and that means we have like first, I don't know, like 90 edges are graph number 0, then we have graph number 1, then graph number 2, etc. All the edges and x's are just stacked together. So initially we had 2 by something for each graph, and we just stack them together. That means that 382 is the number of all the edges within these 4 graphs. 93 by 3 means there are 93 nodes in these 4 graphs, and we have 4 labels, and that's it. And PTR is just an index of where we have the starting point of graph number 1, graph number 2, etc. within this array. That's pretty simple. Okay, let's now construct the simple graph neural net model. We import some PyTorch basics like a neural net module and some functional module. And for PyTorch Geometric, we import a layer called GCN-conv, which is basically graph convolution, and global mean pooling for pooling all the nodes inside our graph. Within GCN-conv, the message passing protocol is already implemented somehow, according to some paper. So GCN-conv, you can think of it as a layer which takes graph as input and produces another graph with new features. Let's start creating our model. Pretty usual thing. We create a constructor. In constructor, we create these convolution operators with this layer GCN-conv. Again, this GCN-conv takes one graph with some feature vectors and produce another graph with other feature vectors. And we need to specify the dimensions of these feature vectors. Input dim will be taken from our data set, and output dim, the size of the output feature vectors, let's say 64. And we create 3 more layers. And in the end, after 3 convolutional layers, we will have the same graph, but each feature vector will have dimension 64. And also after that, we will do some linear transformation after we aggregate all the nodes. We will just do some like final layer, some final linear transformation to produce the vector with size of number of classes to do the final classification. And let's create forward. So for forward, like our inference operation, we will have x. X is usually for data, for features, for our nodes. And edge index. Edge index is basically 2 by number of edges matrix. And we also have this batch thing, which will need it, as we saw previously, for distinguishing between the graphs within a batch. We pass x and edge index to our convolutional layer, and it produces the same graph, basically the same x, so the same graph, but with different x, sorry. The edges will be preserved, edges do not change, but features will be transformed somehow. And the convolution does not include any nonlinear activation function, so that's why we have this ReLU function here. But we have new features as output. Second layer, third layer, for this time let's not use activation function because it's our last convolutional layer. And again, we have the same graph and some features, but new features. Now we can apply global mean pooling, meaning that as input we have graph, but as output we already have just some features for the whole graph, aggregated from all the nodes. And here you can see that we also pass batch. And the question to you, how do you think, why we didn't pass batch to convolutional layers, but we passed batch to global mean pooling? How do you think?
Because the convolutions operation doesn't do anything to unconnect nodes, but the global mean pooling does.
Yep, that's correct. So when we constructed our batch, we should not worry about the connection between the graphs inside that batch because there are just no connections and message passing will just not work. It will not mix information between the graphs. But then when we pass it to global mean pooling, if we do not pass batch, it will just aggregate just one value from all the nodes. But we want a single aggregation per each graph within our batch. And that's why we need to pass batch here. And we apply some linear layer and output this thing. And this is how we construct our model. Just created input dim 3 because the feature dimension of our graph is 3 and number of classes 6. Next, I will really briefly tell you about the training procedure because it's exactly the same as for any other type of neural net. You have your optimizer, you have your loss, you have your loop over epochs, over your batches. I don't know, the only difference would be that your model takes X, age index, and batch, and everything else is exactly the same as for other neural nets. And finally, let's consider a custom way of creating your own layers. For example, I showed you how to use the existing layer, but let's say you want to create your own modification of graph neural network. For this matter, you can create a subclass of this message passing class. There you can create some layers, some trainable operations as much as you can, as much as you like. And then we create a forward function which takes data and edges. And you can start doing some magic here. For example, let's add loops. This is a useful operation commonly used in graph neural nets. For example, usually in your graphs there are no self-loops, meaning there are no connections from edge 1 to, from node 1 to node 1. But for some operations, it is useful to use this thing. So we just pass our edges, and it will create new edges containing these self-loops. Then we can, for each node, we can apply some linear transformation. And then we run this propagate function, which basically runs the message passing for all the nodes of our graph. So here in this forward function, we can do some manipulation on the node level. And then when we did some transformation on node level, we pass it to propagate, and it will start the message passing protocol. We can create our own messages, our own update functions, our own aggregation functions. In this simple case, for example, for messages, we do nothing because we already did some linear transformation. We just pass the message to the xi node from xj to xi. But if we would like to do some transformation over xj's, for example, I don't know, calculate attention mechanism, we can also have not just xj as input to this particular message, but also xi, right? And do some calculations there. And we can calculate the update. For example, we can use RNN within update function or anything else. So, and you can have also a custom aggregation. This is how you create your own graph neural net layers. And that's pretty much it. And finally, I just want to promote you a website related to our NVIDIA developer program when you can have a Deep Learning Institute course and some other interesting SDKs and programs related to deep learning. So just go there and you will see what kind of interesting information is there. And that's it for today. So, yeah, please, any questions?
Okay, everyone, it's time for questions. Thank you. Can we please go back to the slide with the code a little bit back to? Yeah, here. So here you have in the forward x equals f ReLU, and so classically GNNs are defined, two-layer GNNs are defined not the way that they aggregate the information from the same node's neighbors twice, but they aggregate information from two hop neighbors. So is this some sort of different architecture, or?
Well, if I understood you correctly, you mean that in graph neural nets, you want to aggregate not just from neighbors, but from neighbors of neighbors?
Yes, in graph neural nets, layers are defined a little bit differently. And when you say two-layer GNN, that means that you first aggregate information from, like you have a node, you take its one-hop neighbors, and for that neighbors, you also take their neighbors and aggregate information from them. And then you collect for all the neighbors of your target node those features from aggregation or passing through linear layers. And after that, you aggregate again with the feature vector of your target node, and you obtain next layer embedding, maybe representation for your node. So basically, if you have one layer GNN and you pass to the next epoch, that is when you twice aggregate from your one-hop neighbors.
Okay, so the simplest answer would be there are no strict rules in GNNs, right? You can have various different approaches. How can you do this thing? These are just some experiments which are made in some papers. What you're saying, for example, for aggregating neighbors, indeed, you can think of it in two ways. First, if you consider this notation, then after you calculate the second layer, it will also aggregate information from neighboring nodes just because those nodes were already containing this information. Or in another option, you can think of another layer which will, in the first place, in one calculation, aggregate information from several neighbor nodes, not on just one neighborhood.
Yes, but here in the code it is written differently. Here you first aggregate from your neighbors and you obtain the representation for your target node. And again, for the next step, you again aggregate from the same nodes, so those nodes don't get the chance to learn from their neighbors during this time, because you immediately aggregate from after the first iteration again.
Yeah, but within this layer, we have the update function, which will update for neighboring nodes. They will receive updates from their neighbors, right?
But there are two layers just after each other.
Right, but within the conv1 layer, the x which is output, it's the whole graph, right? And for each node, it will already received. Okay. X represents the whole graph. Each node after layer 1 already received from all of its neighbors.
Oh, okay. I thought that X is just a target node or something.
No. So in this notation, X represents the whole graph.
Okay.
Yep.
Thank you.
Thanks for presentation. I have a question. What are the state-of-the-art models on GNNs for unsupervised graph representation learning?
Mm-hmm. Well, so first of all, regarding state-of-the-art, I must say that this is a very rapidly changing thing. I would say that the most loved by researchers of now layers would be graph attention neural networks, graph attention layers. Regarding unsupervised learning, I'm not really sure because it depends on how do you define your unsupervised task. But for example, you can think of, you can formulate unsupervised tasks for graph neural networks similar to any other unsupervised task. You just have a way to pre-process your graph to extract some feature information, and then you can train like autoencoder or do some clustering. So these are like orthogonal things. So you can think of unsupervised learning similar to what is done for other types of data, And for state-of-the-art thing, you can think of a particular layers. And as far as I know, like graph attention networks with attention mechanism are like pretty common right now.
Okay, and what about graph autoencoders? You said also that, yes?
Yeah, you can, I mean, you can construct any type of network using this mechanism, right? So why don't you create graph autoencoder, for example, if you want to train in an unsupervised fashion just features of the graph?
Yeah, I mean features without labels, like they
Yeah.
have...
In autoencoders, you don't have labels, right?
Yeah, yeah. Just asking about, about state-of-the-art.
Well, it depends on your task, because like
Yeah.
unsupervised, there are multiple ways
Yeah.
of creating that.
Okay, thank you.
But mostly it's the same as for other types of neural nets. The only difference would be just the way how do we process graphs from layer to layer, from input to output. But the rest is pretty similar to other types of neural nets.
Thank you for your presentation. I have questions. When you explained the equations about value updates, do you understand correctly that we learn weights for each node, and when we calculate weight for one node and then weight for value for one node and then value for another node, the weights are the same, which are learned.
Right, so all the nodes are updated in parallel, like we do for one node, but we not assign it right away. We calculate the thing which we want to assign to that node, and we do this for all the nodes, and then we do like massive assignment for all the nodes. So they are doing this in parallel.
Okay.
So with the same weights.
And then when we take a batch with several graphs, how do we solve the problem that each graph have different input, right? So each batch can have also different input, and when we want to calculate something in parallel, we should assign for some number of cores for CPU or GPU. How do we distribute it? Do we make some padding?
Well, actually, we don't need to, because when you say each graph has different inputs, it can have different number of nodes, different connections, but the feature vector length is usually the same for each node and for each graph. And you can think of a matrix representing the feature matrix for one graph as this matrix. For example, feature dimension, number of nodes. And then when you construct a batch, you stack by this dimension. So you have the same feature dimension, and then you have number of nodes which are aggregated. And then you use this matrix and you pass it to all your linear algebra, and it is performed in one calculation. You don't need to do some padding
But
here.
input size is always the same. So we stack several graphs in such ways that we have the same input size. Because first, like graph, it's like have 10 nodes and then 20, and so input size is the same.
Yeah, that's correct. So, okay, in this case, you can think of it as a variable batch size. So how to allocate memory, I'm not sure about that. So it's some like low-level mechanism. But in terms of like algebra, you don't need any padding. But in terms of like memory allocation, I'm not so sure how it is done.
And weights, which we learn in each graph, how do they apply? Because we have every new graph is like our new sample, but in which we learn our weights. And with each
not exactly. Weights are not for graph. Weights are for neural net. So the weights are common for everything which we do. Okay. So weights, for example, you can think of a weight matrix is just like, for example, this first matrix will be 3 by 64. It has nothing to do with number of nodes or edges or anything. So weights are just, for example, for second layer, it's 64 by 64, nothing else. It's a single matrix 64 by 64 for everything. Doesn't matter what the batch size is, doesn't matter what number of nodes, etc.
So it's updated, and for next sample, it's the same.
Yeah, it's the same matrix, correct.
Makes sense.
It's
Thank
different between the layers. It could be the same for between layers, for example, in RNN setup, but it could be different for each layer.
Thank you for presentation. I have a question. Whether normalization layers are usually used for GNNs to stabilize training, to improve performance? Maybe there is a specific normalization layer that differs from batch normalization, like in CNNs, or layer normalization, like in transformers.
Well, yeah, actually, good question. There is a special type of normalization in graph neural nets. And for example, this conv layer, which I showed here, is actually same linear operation which was shown here, but with also some normalization. And the normalization works as follows. It depends on how many neighbors does the target node have. For example, if the more neighbors, the less normalization coefficient is. And it is computed via the degree matrix. A degree matrix represents, like for each node, you can have a number of neighboring nodes. And you do some inversion of this matrix, and this is your normalization matrix. So basically, it's used for normalizing the incoming information for different situations. For one situation, you have not so many neighbors. For another situation, you have a lot of neighbors, and you want to normalize between these two situations. So that's why one of the mostly used normalizations is dependent on the number of neighbors. That's a pretty common normalization. Other types of normalization also could be applied, but that's more a specific thing and depends on the specific implementation or a paper. But the degree matrix is usually used for normalizing these things.
Thank you.